This problem and all other practice problems for Calc 2 here at Rutgers can be found in Sarai Studies. A link is in the description box below. Does the following series converge or diverge? Because we're in the integral test section, we're going to be using the integral test, but this can be easily solved in 1 second using the p-test, which I did a video on, so check it out on Sarai Studies. Link is in the description box below. First thing you do is justify your conditions. Like, these are the conditions that need to be met before you use the integral test, but I always leave that to the last thing I do, and I just go straight into the process. So we let f of x be, and you take your sequence, and wherever you see n, you replace that with x, so that's going to be 1 over x. And then all the integral test says is take the limit as it approaches infinity of the integral from whatever number you see here. I see 1, so I'm going to put 1 in there, and then to the n of your function. In this case, that's 1 over x. If it's equal to infinity, then that means that the series diverges. If it's equal to anything that's not infinity, like 1 or 0 or 3, then that means that this series converges. So the antiderivative of 1 over x we know is ln of x. We're evaluating this from 1 to the n. And then fundamental theorem of calculus says take this and plug in n, and then minus, take the same thing and plug in 1. Then we can plug in infinity for n. So we know ln of 1 is just 0, and we know that ln of infinity, well, the limit, if you draw the graph of ln of x, as x approaches infinity, so does the graph approach infinity. So therefore this is infinity. That means that this is equal to infinity, and therefore this series diverges. But before we conclude that, we have to make sure that we were allowed to use the integral test in the first place. So there are 3 conditions that have to be met, and the way that I remember them is that the conditions are literally in the word. So I spell out the word integral, and then I actually make an L, kind of like this, because this is an L, right? So if you have a graph that looks like this, which is literally this, look at it and tell me what it is. Number 1, it's positive because it's above the x-axis. Number 2, it's continuous because it's smooth, right? There's no stopping, no holes, no nothing. And number 3, it's decreasing. It's going downward. And so the conditions are literally in the word integral. Just remember that the L is literally a graph that represents all the conditions of the integral test. And it's also the graph of 1 over n. This is 1 over n. Now, if you have Molnar gives you 1 point for this, 2 points for that, and 3 points for that, at least for my exam in 2024. To prove that it's positive, what are we proving that's positive first of all? This function here. So to prove that this is positive, you just say f of x is positive for all x greater than or equal to, and then whatever number you see here. So that's 1. And it makes sense, right? The only n's that are going to go in there are greater than or equal to 1, and you only have an n here, so in this case n and x equivalent, so therefore your function is going to be always positive. To prove that this function is continuous, well, what does it mean for a function to be continuous? Well, it means that it has no holes, it's smooth, there's no cusps, it's defined at every point. So that's the one that I use. I make sure that no matter what x value I can put in, it's always going to be defined. So I say f of x is continuous for, and then I do the exact same thing, greater than or equal to whatever number's here, keeping in mind that it's because f of x is defined for all x is greater than or equal to 1. Because what makes it undefined is 0. So if this was n is equal to 0 instead of 1, then we wouldn't be able to use the integral test because the function would not be defined at every single point because we would be plugging in 0. And then the last thing is you have to prove that this function is decreasing. Now, well, remember the relationship between a function and its derivative. If a function is decreasing within a certain interval, then within that same interval, the derivative of that function is going to be negative below the x-axis. For example, let's say I have a function that looks like this. I clearly see that it's decreasing the entire time. So then that must mean that its derivative, which looks like this, is going to be below the x-axis the entire time. So if the function is decreasing that entire time, then that must mean that the derivative of the function is going to be below the x-axis the entire time. So essentially, we're going to get our function, we're going to find its derivative, and we're going to make sure it's negative because then we can say that we know that the function decreases, and that's what we want. We want the function to decrease. So that's the logic behind that. So we have f of x is equal to 1 over x. F prime of x is going to be equal to negative 1 over x squared. Just use the quotient rule. It's f prime g minus f g prime over g squared. So we plug in what we have. F is my numerator. G is my denominator. Derivative of f is 0. Derivative of x is 1. Then we plug in our stuff in here. So because f prime of x is 0, that means that 0 multiplied by g is still going to be 0, so none of this matters. F is just 1. This is really just 1 over g squared, which is just x squared, and that is my derivative. And because the derivative is always negative, meaning it's always going to be below the x-axis, then I can say that the function is decreasing. If it's negative, that must mean that the function is decreasing. F of x is decreasing because f prime of x is equal to that. that, and it's always negative. And those are all of our conditions justified. For a conclusion, we say since, and then we mention all of our conditions. F of x is equal to 1 over x is positive, continuous, and decreasing for all x is greater than or equal to 1, and then you write the limit is equal to infinity. The integral test implies the given series diverges. So this series diverges. We also could have used the p-test because this is in the form of 1 over n to the p, where p is equal to 1. We know the rule that PG-13, or movie rating, p greater than 1 converges, and then the opposite diverges. Because p is equal to 1, then that means that this series diverges. See, so using the p-test takes 1 second, but if you're told to use the integral test, then you gotta do all this work just to prove the same thing.